Hi, a good day to all attendees. Welcome to the webinar on multi-physics modeling for oil and gas application. My name is Mattia Sulis, and I'm very excited to be conducting this webinar today. I have been with Convergent Science for almost 10 years now, and my focus is on connecting with other CFD users and show them a more efficient way of doing CFD. Before I move with the presentation, a quick note. During today's webinar, if you have any question, please use the question box on the GoToWebinar toolbox. Questions submitted during the webinar will be answered at the end. I would like to start with a quick introduction to Convergent Science and Converge CFD software. Convergent Science develops and supports CONVERGE, a state-of-the-art CFD software designed for fast, predictive multi-physics simulation in complex geometries. The company is headquartered in Madison, Wisconsin, and then offices in United States, Europe, and India. As of today, the CSI team is composed of over 150 people globally, and we continue to grow. CONVERGE revolutionized the CFD industry by introducing fully autonomous meshing. These features significantly reduce case setup time, accelerating the simulation process and saving clients both time and money. Over the past 25+ years of business, CONVERGE has served the computational fluid dynamics community in many industries. This is the fourth webinar of our 2023 webinar series. As you will learn in today's session, as well as from our previous one, CONVERGE is a great tool for a number of applications, like pumps, compressor, batteries, e-motors, wind turbine, and much more, including the one that will be featured in upcoming webinars, biomedical in May, and after-treatment system in June. This is what we are going to cover in this webinar. 4 cases. Sloshing tank, capping stack placement, PDC drill bit performance, and resolved porous media. With the sloshing tank case, we will show how liquid-gas interface tracking works in CONVERGE. In the capping stack placement case, you will learn more about the FSI model. When we will talk about the polycrystalline diamond compact drill bit case, we will introduce a new erosion model available in CONVERGE. Finally, the resolved porous media example will show how CONVERGE is uniquely suited to run every complex geometry with its transfer. In the picture below, you can see a quick preview of all these simulations. From the left, we have the sloshing tank, the capping stack, the drill bit, and finally, the resolved porous media. Before we dive into those 4 examples, I would like to take a few minutes and introduce more details about CONVERGE autonomous mesh and its array or advanced physical model. First, allow me to introduce to you the mesh process in CONVERGE. CONVERGE automatically generates a body-fitted volume mesh using a patent cut cell technique. This means that as a CONVERGE user, you will not spend any time creating a mesh, as that is done by the solver at runtime. Even though the mesh creation is automated, as the user, you will still have full control on the mesh size and the refinement level. You can do that by setting up first the base mesh. The base mesh size is the largest grid size available in the simulation. And then, on top of that, you can set up fixed embedding and adaptive mesh refinement, or AMR. As you can see from the video example below, CONVERGE will automatically refine the mesh in those areas with local gradients. In this way, there will be fine mesh only where and when it's necessary. This will reduce the total cell count and improve the runtime of the overall simulation. When it comes to running a realistic CFD simulation, CONVERGE offers many physical models, as you can see from the screenshots taken from CONVERGE Studio. In the next 4 examples featured in this webinar, we will focus on volume of fluid model, or VOF, conjugate T transfer, or CHT, fluid structure interaction, or FSI, erosion, and porous media with heat transfer. However, many more are available. So if you have a CFD problem with complicated physics and or complex moving geometry, we are here, ready for you and your CFD problem. The first case study that we will explore today is a sloshing tank case. There are several industries interested in this type of problem. To name a few, oil and gas, of course, aerospace, automotive, and water management. In the video that you see on the right, a tank at zero gravitational force is moving in alternating direction. You can see how the liquid in green, starting from a resting position all around the tank, reacts to a motion and later on forms a bubble. The CONVERGE simulation is compared to the real experiment that was performed at the International Space Station. CONVERGE is able to accurately reproduce the liquid motion and the formation of the bubble. Then it accurately predicts how the bubble detaches from the rest of the liquid. In this video, you can also see how AMR is refining the mesh automatically at the interface. In the 4 case studies that we have prepared for you today, you will see multiple examples of how AMR works and how CONVERGE reduces simulation time through the use of adaptive mesh refinement. These are the details of the sloshing tank case that will run for this webinar. We consider the initial liquid orientation of 5 degrees. We consider 6 HOR ratio, and you can see in the picture below the 6 different initial levels for the liquid. Gravity is enabled, the base mesh is 8 mm, and on top of that, we set up a fixed embedding that refines the mesh at the interface at the start of the simulation. AMR is also enabled on void fraction and species mass fraction, in this case on water. In the next few slides, I'm going to dive into few results and 2 sensitivity analyses. The first comparison is for the same setup, but different HOR ratio. All the CONVERGE results are compared to an empirical correlation from the NASA SP106 paper. This correlation is valid only for HOR values greater than 1. As shown in the plot, CONVERGE is in good agreement with the reference data for HOR equal to 0.25, 0.5, 1, and 2. The results start to deviate from the reference for the 2 extreme value of HOR, as expected. In this video, you can see the flow evolution inside the tank for all 6 cases. The videos are synchronized, so it is easier to spot the differences. In the first case on the left and the last one on the right, you can see how the liquid is interacting with the bottom and the top surface of the tank. The videos show a cut plane through the center of the tank. The planes are colored by density. Blue represents water and red is air. You can spot some differences as the flow evolves. The video on the left with HOR equal to 0.125 shows the fluid motion is quickly influenced by interaction with the sidewall. The same can be seen for the video on the right with HOR equal to 2.875. As the value of HOR increases, you can also notice how it takes longer time for the liquid to reach a steady state. It is interesting to see how for the 2 lower value of HOR, 0.125 and 0.25, the ripple effect is more evident. Furthermore, in the case of HOR 0.125, you can see the breaking waves right at the beginning, around 1.2 seconds. As the video keeps playing, a quick reminder, if you have any question, please put them in the question box and we will address them later in the video. The first sensitivity analysis that I'm presenting is based on the AMR refinement level. This level of refinement is based on the base mesh, as always in CONVERGE. The base mesh for all these cases is 8 mm. Refinement level is calculated as base mesh divided by the refinement level raised by the power of 2. Refinement level 2 means a cell size equal to 2 mm. Refinement level 3 means a cell size equal to 1 mm. You can see how both cases show good agreement with the reference data. This means the grid convergence was reached for this case. When you take a closer look at the videos, you can notice the fixed embedding at the interface at the start of the simulation. As the simulation proceeds, you see then the AMR refining the mesh on the fly exactly at the interface between the two species. In the lower video, related to the case with AMR level 3, you can clearly see how more cells are created by AMR, especially in the part of the domain occupied by air. The second sensitivity analysis that I'm presenting is based on the surface compression model. When the surface compression model is enabled, source terms are added to the species density, mixture momentum, and mixture energy transport equation. The surface compression model is a tool available in Converge when a sharper interface is a requirement for the simulation. In the two videos, you can see a slightly sharper interface for the case at the bottom, the one where the surface compression model is enabled. You can also see how the AMR is behaving differently for the two cases. In the case with surface compression enabled, AMR is less active and the total cell count is lower. This results in a faster runtime. The case with surface compression off took about 16 hours to run. Meanwhile, the case with surface compression on took about 4.5 hours less, around 11.8 hours total. However, these cases show more deviation for the reference data, as you can see from the plots on the right. In the zoom plot, you can see how the light green curve related to the case with surface compression on goes beyond the black one, calculated using the empirical equation mentioned before. In summary, with surface compression, the simulation will have a faster runtime, but there will be an impact on the accuracy. Continuing with surface compression model, these other sensitivity studies show the effect of increasing the surface compression factor. As you can see from comparing the two videos, the interface sharpness increases slightly as the surface compression factor is increased. However, there is a cost associated to the sharper interface. The accuracy is impacted even further. It is clear from the zoom plot how the case with surface compression factor equal to 0.5, represented with the light blue curve, is deviating more from the reference data. From the previous slide, the case without the surface compression model had the runtime equal to 16 hours. Once surface compression is enabled, the runtime is reduced to 11.8 hours for a surface compression factor equal to 0.25. And it goes down to 9.5 hours for a compression factor equal to 0.5. The user has the ability to choose which approach is more valid depending on the simulation objective. Longer runtime with more accurate flow behavior, or a shorter runtime, sharper interface, but less accurate overall flow behavior. The second case study that we will look today is a capping stack. Before going into the technical details of this case in Converge, I would like to go through this very quick introduction. You might have heard of the oil spill at the Deepwater Horizon oil rig in 2010. In that specific accident, the blowout preventer failed to seal the well. As an attempt to stop the flow, a capping stack was successfully used a couple of months after the initial event. In this slide, I summarize the timeline of the oil spill. Different techniques and different devices were used trying to slow down the oil flow or to stop it altogether. In May, a top kill approach was used and the procedure was unsuccessful. In June, a new attempt was made using different types of cap containment systems, but the flow was now completely stopped. In July, that's when a capping stack was used to stop the flow. There you can see a schematic representation of the blowout preventer in brown and in black, and the cap assembly that was placed on top in orange. This procedure was successful and it helped slowing down the oil flow. Finally, in September, the well was officially sealed. CFD can be used to help modeling the underwater motion of the cap and its interaction with the blowout jet. Converge, its autonomous mesh and advanced FSI model are well suited for this type of simulation. Some of the CFD simulation requirements are: simulation need to be transient, a VF model is required, plus a model to implement the mooring cable motion should be considered. As you can see from the video on the right, in Converge you can have this multi-physics approach, plus there is no overhead for the user due to the geometry motion. Again, if you look at the video closely, you will see how CONVERGE can handle the complex motion of the geometry as a result of the interaction with the mooring cable and the jet. These are the case details. AMR was enabled for velocity, void fraction, and mass fraction. The capping stack body was treated as an FSI object with 6 degrees of freedom. And we use the RNG K-epsilon turbulence model. On the right, you can see a screenshot of the case setup doc in CONVERGE Studio. CONVERGE Studio is a preprocessor that comes with a Convergent solver and that is included in your license package. With this user interface, you can import any native CAD file and you can set up the case from start to end. This is a video of the CONVERGE simulation we ran. The total cell count reached a maximum of 4 million. As AMR was enabled, the total cell count oscillated during the simulation from a minimum of 200,000 to a maximum of 4 million. We ran the simulation on Converge Horizon, our cloud platform. On Converge Horizon, different hardware configurations are available. One of them is the 128 course node with 2 TB of memory, and that's what we use for the simulation. The simulation considered 50 seconds of physical time, and it took about 66 hours to run. First, I would like to point out how the mesh adapted at runtime to the motion of the capping stack. Second, you can see again in these examples how the AMR is refining the mesh on the fly based on quantities that the user specified. Finally, you can see how the mooring cable model, the FSI model, and the VOF model are working together to predict all the physics of the real problem. This is another video along with the still image of the mesh that show the full mooring cable in addition to the capping stack. On the video on the left, you can see 2 contours planes. One, the show alpha, the void fraction, which is the gaseous fraction of the volume of a cell. The other plane, on the right of the video, show velocity magnitude. In this view, you can also see the turbulent structure modeled by CONVERGE as the blowout jet moves away from the well. You can also notice how the different length scale can be easily modeled in CONVERGE, ranging from the small scales near the well to the bigger ones away from the capping stack body and the well. The third case study for today's webinar is a polycrystalline diamond compact, or PDC, drill bit. I'm going to start with an animation from Converge Studio to describe this case. In Converge Studio, once the case setup is complete, you can create an animation of a moving geometry. This is before you start your CFD simulation in Converge. It allows you to check how the geometry is moving and how to make sure that the motion is consistent with the real problem. As anticipated at the beginning of the presentation, the erosion model is enabled in this case. In addition to this, we also consider conjugate heat transfer and solid parcels. Now, I'm going to spend a few minutes introducing each of these models. The conjugate heat transfer model allows you to predict the heat transfer within and between solid and fluid simultaneously. Transport equations are solved in fluid and solid domains with coupling at the interface between them. As you might be aware, the timescale necessary to resolve solid heat transfer is usually greater than the one for fluid heat transfer. In order to efficiently model this disparity in timescale, CONVERGE offers a supercycling method. The example on the right shows the CHT model applied to an electric motor. As you can see, the temperature in the stator gradually increases from the initial value to the steady state one. Let me use one slide to explain how the supercycling model works. In summary, the supercycling method accelerates simulations of both steady state and transient solid temperature. In details, it iterates between fully coupled fluid with solid transient simulation and isolated solid simulation. In the fully coupled phase, it solves the fluid and the solid heat transfer together using the transient solver. Periodically, it freezes the fluid solver to solve for the isolated solid temperature. It uses the updated solid temperature to solve for the fluid and the solid using the transient solver. Finally, it repeats until the solid temperature converges. In the image on the top right corner, you can see the temperature distribution in the battery pack as thermal runaway is occurring. In the video on the bottom right, you can see how CHT model in conjunction with supercycling is used to model the warm-up phase on a plug-in hybrid vehicle battery pack. The next model featured in this case that I would like to introduce is the one for solid parcel. In CONVERGE, a parcel represents a collection of solid, liquid, or gas particles. Solid parcels modeling include parcel-parcel interaction, and it can be combined with radiation modeling and erosion modeling. On the right, you can see how the solid parcel model can be set up in CONVERGE Studio. At the bottom right corner, you can see a still image of an example that includes both the solid and liquid parcel. Finally, let me spend a moment describing the erosion model in CONVERGE. Solid parcel and erosion modeling can be combined in order to capture the erosive effect of a solid impinging object on a surface. Please note that with this model, the surface geometry in the CFD simulation remains unchanged. Erosion is computed through the erosion ratio ER, which represents the ratio of mass eroded to the mass impinged. In the plot on the top right corner, you can see the validation study that we run and the comparison with the experiment from Zhang et al. 2007. At the bottom, you can see a video of that same simulation. There, we show the solid particle and the geometry surface is colored with erosion model, mass eroded, and the mass impinged. Now, it is time to talk about the case setup in CONVERGE. On the right, you can see several screenshots from CONVERGE Studio that show the geometry from different angles. The drill bit is moving at 50 RPM. We impose the inflow boundary condition as a mass flow. And on the other hand, we have a pressure boundary condition at the outflow. In regards of the fluid property, we consider the fluid as non-Newtonian using the Herschel-Berkeley model. When the erosion model is enabled, in combination with CHT and solid parcel, CONVERGE can be used to calculate mass impinged and temperature in the drill body, for example. In the video on the right, you can see the PDC drill bit body moving and colored by temperature. The temperature increases is correlated to the frictional heat flux. The video also shows the solid parcel within the domain. The solid parcel represents the cutting being carried away by the flow. In addition to the data shown in my previous slide, it is also possible to calculate the mass eroded. The video on the right shows the drill bit body colored by the eroded mass. The red spots represent the areas with higher values of this mass. The eroded mass is the one due to the solid cutting. On the plot on the left, you can see the evolution of the eroded mass over time. The fourth and last case study that my colleague in the application and development team helped put together is a resolved porous media. This example considers a real subterranean scan as the geometry for the CFD simulation. The objective of this simulation is to calculate the necessary coefficient for an unresolved porous media simulation. In particular, the coefficient that we are more interested in this case is the fluid solid HTC that can be used for your local thermal non-equilibrium model that is available in CONVERGE, for example. In addition to this, we are interested in the alpha and beta porous coefficient. In general, as a CFD user, you are relying on multiple assumptions in order to calculate this coefficient. In CONVERGE, you can take the guesswork out of your workflow and run a resolved porous media case to be more accurate in your production type everyday simulation. After loading the raw CAD file in Converge, you will be able to use the CAD tools in Converge Studio to prepare the geometry. For this case, we initially coarsened the geometry, but kept the difference under 0.05% between the original and the new one. Other tools in Converge Studio were used to repaint intersection and other defects present in the original CAD. The final result was one surface file with 22 million triangles. From the pressure drop and associated fluid velocity, it is possible to determine the porous media model coefficient. The contours on the right show pressure and velocity value across the domain for two different applied pressure gradients. On the left, you can see the two cases, the contours for a pressure gradient equal to 1 kilopascal. Meanwhile, on the right, we show the same contours, the same cut plane for a pressure gradient of 3 kilopascal. Now it is time to wrap up this webinar. If you have not done it so already, please use the 2 QR code here to reach our Contact Us page and to sign to our newsletter. Our newsletter will feature all the news around Converge, including future webinars, upcoming trade show, and the training schedule. In terms of what's next, the first event that I would like to share with you is the next installment in our webinar series on May 3rd. It will focus on biomedical application. The title is Assessing the Performance of a Medical Heart Valve Through Simulation. The registration link is available on our website. Please go ahead and register today. Finally, I would like to quickly mention that we will have a booth at the upcoming Offshore Technology Conference. The event will take place in Houston, Texas, between May 1st and May 4th. My colleague, Dan and William, will be there to answer all your questions about Converge. Thank you all for joining today's webinar and for your interest in Converge. Please reach out to us if you'd like to have more information about Converge and visit our website, convergecfd.com, to view more examples of Converge. You can also create an account and access our free on-demand training videos, including fluid structure interaction modeling, volume of fluid modeling, and compressor and pumps modeling. Have a great rest of the day.